So that was t-tests, as I said, probably the most popular test in statistics, but they're only suitable for normally distributed data. So if you're in a situation where the data are not normal, there are other tests that are available. So if you were to do your histogram and you got something like that, I mean, these frequencies are quite high, so that's clearly not a normal distribution. Nor is this one, it's quite skewed to the left. So if you're in that situation, as I said, first of all, you might want to try a transformation of the data, such as using a log and rechecking the histogram, because it's always better if you can do a t-test. But if you just can't do that, you're going to have to move to the first of the non-parametric tests that we're going to look at. The non-parametric tests have even more obscure names than the parametric tests. They're quite often named after people who first suggested them. So this test is known as the Mann-Whitney U-Test. Confusingly, it was also the equivalent test was suggested by someone called Wilcoxon as well. So sometimes you'll see it's referred to as a Wilcoxon rank sum test. So it's worth remembering that they're really exactly the same test, but I'll talk about it as the Mann-Whitney U-Test. And the U comes in because the statistic, that when it was calculated by hand, there was something they called the statistic they came up with as a test statistic, a U statistic, so a bit meaningless really, but this name is kind of stuck for the test. So that's suitable for non-normal data, and as I said, it's the first example we've got of a non-parametric test. So how do non-parametric tests work? I mean, whoever came up with the idea, it was a clever way to analyse the data. It's simply based on, rather than using the original scale of the data, using the ranks of the data. So if you put the data in order, you work with their ranks. So if this is hypothetical data, if we'd got two small groups of 4 values, Group A and Group B, and we wanted to compare them, and we knew that they weren't normally distributed, or we couldn't be sure they were normally distributed. The way we'd start off is we'd put them in order, and if we ranked them, counting here the smallest one, give it rank 1, up to the largest value, 35, is given rank 8. So these are the ranks of the data, and it's irrespective of what group they're in. We're ranking all 8 values, so if we're going to have a rank of 1 to 8. And what the test seeks to do is says are the ranks for Group A statistically different to the ranks for Group B. And I'll not go into all the calculations, but basically this, just like the t-test, can be done in a statistical package, and the package will come out with a p-value. And for this data, coincidentally, it's the same as the last p-value. We got a p-value of 0.06, so not quite enough information to show that these ranks are statistically different to these ones. So the difference about this is we're working with the ranks, not the actual data. If we were to work with the actual data and do a t-test, we might find if we got some extreme values, they would really skew the results and not be a sensible thing to do. So this is an example of some output from Minitab. It gives us what's known as the median, and if you remember from last time, that's the middle value. It gives us the middle value for each of the groups. I won't go into explaining what this eta 1 minus eta 2 is. Well, it's basically the difference, but they're using eta as another example of a Greek symbol that for some reason the package is unable to produce. The key thing is the p-value, and it doesn't say p-value, but hopefully you'll realise it's doing the test and it's saying it's significant at. So it says it's significant at this p-value, which even though it's not significant, it's basically saying the p-value is 0.06. Sometimes the package output is either not useful or not described very well, but the main thing is that you understand your package enough to get out the information you want from it, which in many cases is the p-value from the statistical test. So to summarise a few general points about the Mann-Whitney U-Test, remember this is the equivalent of the t-test for parametric data to compare two groups. So it's suitable for any continuous data, and it can be used with non-normal data, used for comparing two independent groups. We'll be looking at next something called, for paired data, called the Wilcoxon signed rank test, but we'll leave that for the next slide. I think I've said this already, ranks take no account of the sizes of the differences on the original scale. You're just working with their ranks. And if your data are normally distributed, it is better to do a t-test because you're taking account of the scale of the data. So don't sort of think the Mann-Whitney U-Test is always appropriate. I may as well always use it because it's never going to be wrong. It'll be less sensitive if you have got normally distributed data. So I'd use the t-test if you can. Sometimes you've got non-normal data and it's actually paired. So just as the example we looked at before, you might have animals where there's a measurement taken before treatment and after treatment. Both the measurements they're both non-normal. And the best thing to do, is, again, just as with the paired t-test, is to work with the differences. So you take the differences in the values, but because this is not normally distributed, we're going to work with the ranks of the differences. So you take you rank these differences, and for this particular test, any differences of 0 are just ignored. So the differences are ranked, and we don't need to know about this step, but you sign the ranks so that depending on the absolute difference, some of the ranks, if there was a minus value before, then the ranks get signed, you get a negative sign applied to that. And you want to be testing whether these ranks are significantly different from 0, the signed ranks. And so this test, known as the Wilcoxon signed rank test, which I won't go into the details of how it's calculated, it's quite a clever calculation, will test whether these signed ranks are significantly different from 0 overall. And this is the output that would have been obtained from Minitab. And you'll get used to sort of homing in on the thing you want to know, which is what's the p-value? Have I got statistical significance? And here we have got statistical significance. P-value, it's less than 0.05. So we've been able to show these values before treatment are different to the values after treatment using this Wilcoxon signed rank test.